The nature of acids and bases. So we're not going to be using Arrhenius' theory, which is looking at, or which is said that hydrogens are going to be donated by acids and hydroxides are going to be donated by bases. Instead, we're going to be using the Bronsted-Lowry theory. And essentially what this is a bit of more of a generalization of the Arrhenius theory, and it is just focusing on the hydrogen ions themselves. And so it is based not on the formula of the substance as to whether it's an acid or a base, but it's based on how the thing behaves during a reaction, so like a chemical property. And what this is going to allow us to do as well is look at these things called conjugate acid-base pairs, and really all they are is looking at something that is transferring a proton, also known as a hydrogen ion, and it is that transfer of that proton that defines a reaction as an acid-base reaction. So for example, if we have HCl here, it by itself wouldn't be an acid. However, it can act like an acid in a particular reaction. So here it is reacting with water, and we can see that the HCl becomes just the chloride ion. So essentially it has given up its hydrogen, and that's how we're going to define an acid under the Bronsted-Lowry definition. And in this case here, if we look at water, water starts off as H2O, and then it becomes a hydronium ion. It's picked up that hydrogen ion. So essentially the transfer of the hydrogen ion went from the HCl over to the H2O, and then we got this new combination of a chloride and a hydronium ion. So essentially in this scenario, anything that donates protons is a Bronsted-Lowry acid. In this case, HCl is doing that, so it's the acid. Because in this particular case, the water is accepting a proton, it is defined as a Bronsted-Lowry base. And so under the Bronsted-Lowry definition of acids bases, things that donate protons are acids, things that accept protons are bases. Another example here that would not work with the Arrhenius theory, and so here if we look at this ammonia, at the beginning of the reaction it's NH3, at the end of the reaction it is NH4 positive. It has picked up a hydrogen ion, and according to the Bronsted-Lowry theory, things that do that, things that pick up hydrogen ions, they are bases. And in this case here, water started off with its two hydrogens there, and it has given up a positive hydrogen ion to become hydroxide, and therefore it would be defining as a base. So the ammonia is, sorry, I said that wrong. The ammonia is the base because it is the one that is accepting the proton. In this case, the water, try to get it right this time, the water is donating its hydrogen, and so that is going to make it a Bronsted-Lowry acid. Acids donate protons, bases accept them. So here we have the two reactions together, and what I want to draw your attention to is the waters. In both cases, we have water acting in a different way. And so in the first case here, water becomes hydronium, it picks up a hydrogen. And in the second case, water donates a hydrogen and becomes hydroxide. So again, water is not inherently an acid or a base, but depending on which case you're talking about, depending on the situation, it can do either. And so they get the special term called amphoteric, substances that can either donate a hydrogen or accept a hydrogen in two different circumstances. They are referred to as amphoteric. Now, of course, they'd have to have a hydrogen in their formula in order to do that, but if they do have that hydrogen, and in some cases they donate it, other cases they will accept someone else's hydrogen, they are referred to as amphoteric. They are both a Bronsted-Lowry acid in one case, and in another case a Bronsted-Lowry base. So acid-base reactions, these will establish an equilibrium. We'll talk further about strong acids and bases and weak acids and bases in our next lesson. But essentially, these certain types of them will reach equilibrium, and that there's going to be a balance between the amount of reactants and the amount of product. Not an equal balance, but there will be some of each, and we can sort of express this as an equilibrium system. So imagine these reactions can go forward and reverse, and so therefore they are going to, they could come to an equilibrium. And when we do this, we can look at either side of the reaction, we can pair them up, and we refer to these as conjugate pairs. Essentially what the thing was, either the acid or the base, what it was at the beginning of the reaction, and then who would become at the end of the reaction, they will make up a conjugate pair. Their only difference between them is going to be that on one side they're going to have the proton, on the other side they're going to not have the proton. So for example, if you take acetic acid and you put it in water, as the name would suggest, this is an acid. This is an acetate ion with a acetate ion with a hydrogen ion as well, and it can give that hydrogen to water. And in that case, it's going to leave behind an acetate, and now the water is going to have that extra hydrogen and it'll become hydronium. So if we look at the beginning of the reaction, there's our acetic acid, and then at the end of the reaction, it is only different by its lack of its proton because it's donated it. It's an acid, that's what it did. And then we have this other substance here, water. At the beginning, it has just 2 hydrogens. At the end, it has 3. So there's our pairs there. So we're going to refer to those as conjugate pairs. And of course, we have our acetic acid. This is an acid because it starts off with its hydrogen, and then it donates it to become this acetate ion without the hydrogen. And then we have our base. In this case, our water is acting as a Bronsted-Lowry base, and its conjugate partner is the hydronium ion, which now has that extra hydrogen. So the conjugate partners are going to be on the other side of it. They're going to be pairing up. So the acid's conjugate partner, the acetic acid's conjugate partner, is going to be acetate, and it is a conjugate partner. And specifically, if you think of the acetate as going back to form the acetic acid, what it would have to do that would be to pick up a hydrogen. And we know that things that pick up hydrogens, those are called Bronsted-Lowry bases. So this is a conjugate partner, and in this case, the acetate is the base. So the acid's conjugate partner is a base. And of course, then the base's conjugate partner, because if you imagine the hydronium went back and reformed the water, then it would be donating it. So its conjugate partner would be an acid. So water in this case is a base because it will pick up a hydrogen and become a hydronium ion. But then if the hydronium were to reverse, if this were to be an equilibrium system and it were to be going backwards at the same time, then that hydronium ion would be a conjugate acid to its partner, the base. So we have our acid and its conjugate partner, which is a base. Then we have our base and its conjugate partner that is an acid. And this is how we can define conjugate partners in an acid-base reaction. What we can then do is we can look at these as a equilibrium system. And so if we just used the generic expression for a acid, it has to have a hydrogen, and then whatever the other anion is part of it. So we could often just say HA to represent some generic acid. That A could be a chloride ion, or it could be a acetic acid ion, whatever it happens to be. And if we're talking about weak acids, there'll be certain ones that it will be. But essentially, if it breaks up, it gives up its proton. That proton can be picked up by something. So this is how we can generally write the equilibrium expression for a weak acid. Now, because it's at equilibrium, we can think about the equilibrium constant for this reaction just like any other equilibrium reaction. To be a little bit more accurate, we should really say who is picking up that hydrogen, because the acid won't just let go of its hydrogen ion. It will have to, it'll hang on to it until something takes it. And so in this case here, water is going to be taking the hydrogen ion, and then we're going to form hydronium. So really this is the proper way to look at a generic acid reaction, but because we're talking about water as a liquid, we know that if we were to write the equilibrium expression, it's not going to show up in there. So quite often people don't write the water and then they just write the hydrogen ion instead of the hydronium ion, just being lazy. But that same idea. So if we were to write the equilibrium expression, it would look like so, that the products of the reaction, just like any other equilibrium expression, but in this case the products are the hydronium ions and the conjugate partner of the acid in this case, and it would be a weak acid if we're talking about equilibrium here, otherwise it'd be so far to the right it wouldn't be worth talking about equilibrium. So we have our products over our reactants, concentration of products over our concentration of reactants, and remember, because water's concentration doesn't change, it doesn't show up in the denominator here, so we just have the concentration of the original acid. And this will give us what's called the acid ionization constant, or our K value, just like any other equilibrium expression. It's got a K value for it. And because acids are a particular important type of reaction when we talk about them, we give it the subscript A, and we refer to this as the acid ionization constant.